Welcome! Let's take a look at connecting the notion of area under the curve with velocity and distance. Kim is walking downhill such that her velocity varies according to the measurements in the table and the graph. So in the table, we see Kim's velocity in increments of a quarter of an hour up to 2 hours. And we can see her velocity as well for each corresponding time. And then to our right, we have the graph that illustrates her velocity as a continuous curve. And what we want to do is use the information provided to estimate the distance that Kim walked over a 2-hour period from t equals 0 to t equals 2. We're going to use a time interval of 0.5 hours to find the approximate distance that Kim walked. Let's zoom in on the graph here for a moment. We're interested in how far Kim walked in 2 hours. So this time interval as indicated on the horizontal axis. And note that our vertical axis is labeled in terms of miles per hour, and our horizontal axis is measured in hours. So if we were thinking to approximate the distance that Kim walked, we could use rectangles to help us do that. Now, we were instructed to use intervals of 0.5 hours or a half an hour. So going along my horizontal axis, there's the first half hour, there's the second half hour, there's a third half hour, and there's a fourth half hour. So we'll start by considering creating rectangles, and there's a variety of ways we could create a rectangle. But let's go ahead and use the function value at the left endpoint of the interval. So I'm going to have rectangles that look like this. And again, we're using the function value at the left endpoint of the rectangle. Of the interval. And so continuing on, we're going to end up using 4 rectangles because the interval length of 0.5 hours created 4 sub-intervals for us. And so what we're going to do for each of these intervals, or each of these rectangles, we're going to find the area by considering length times, or base times height. Base times height for each one of these. So area of the first one, area of the second, base times height, area of the third, base times height, and area of the fourth, base times height. And we'll sum those all together, and that will give us an approximation for the actual distance that she walked, keeping in mind that the actual distance is this shaded area under the curve. So notice there will be some area, there are some gaps that we're not going to capture. They're in green, and here, and a little bit there, and a little more here. However, it will be a fairly decent estimate, it appears. So let's go ahead and do that. So the distance that Kim is walking is going to be the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4. And so this is equal to, now keep in mind we're using the function value at the left endpoint for the height. So the velocity at time 0 is 1.75. So the height of that rectangle is 1.75 miles per hour. And the base of that rectangle is half an hour, or 0.5 hours. So 0.5 hours. That's area of rectangle 1, plus for rectangle 2, the height is the velocity at 0.5 hours. Our velocity at 0.5 hours is 2.22. And the base of our rectangle, again, is 0.5 hours. So we're going to have 0.5 hours times 2.22 miles per hour. Moving on to rectangle 3, we're interested in the velocity at 1 hour. The velocity at 1 hour is 2.25, and of course the base of our rectangle is still half an hour. So 0.5 hours times 2.25 miles per hour, and plus the area of our fourth rectangle. Again, the base is going to be half an hour, 0.5 hours, and the height of this rectangle is the velocity at 1.5 hours, and that is 2.41 miles per hour. So we'll have 0.5 hours times 2.41 miles per hour. Now we can go through and we can see that based on our units, we're adding a bunch of miles together. So each of these is an estimate, each of these products is an estimate of the distance that Kim walked in that half hour. And so if I multiply all of these together and sum them up, we can see that Kim walked approximately 4.315 miles in the 2 hours. Now, notice though that we mentioned there was an error, that there's these pieces of distance that we haven't captured in our estimate. And notice also that our velocity function is an increasing function. So we can say that since the velocity function is increasing, when I create these rectangles using the left endpoints for an increasing function, I will have some error. I will have an estimate, but it's an underestimate because I'm not capturing all of the entire distance that's being traveled. And that's because we're using a left endpoint to create our estimate, and our function is increasing. So since our function is increasing, we're going to call this L4. It's a left estimate, left endpoint estimate, using 4 intervals. Is an underestimate, meaning that Kim actually walked a further distance that we didn't capture in our estimate. Now we can, instead of using the left endpoints, we could use the right endpoints of each of our half-hour intervals. So let's take a look at what that might look like. Since we're going to use the right endpoint of each of our time intervals, we'll be using the height of the velocity function at 0.5 hours or half an hour to create our first rectangle. We'll use the height of the velocity function at 1 hour to create our second rectangle. the height of the velocity function at 1.5 hours to create the third rectangle, and then the height of the velocity function at 2 hours to create the height of our last rectangle. Notice that in this case, when we find the area of each of those rectangles in order to estimate the distance traveled, this time we're going to have a bit of an overestimate because the area of the rectangle surpasses the area underneath the curve. So let's go ahead and approximate the distance this time using the right endpoint of each time interval. So still our distance is going to be approximately the area of the sum of the areas for each of our 3 rectangles. This time when I write out our computation here, I'm not going to worry about including the units. We already know what those units are, and we've seen how they simplify. So I'm just going to write the numerical values. So in doing this, then, the base of the rectangle is still 0.5, and the velocity at half an hour at 0.5 is 2.22. Plus, for my second rectangle, the base of the rectangle is still 0.5. This time I'm using velocity at 1 to get the height of my rectangle, and that is 2.25. The area for the third rectangle, our base is still 0.5 hours. The height of this rectangle is based on velocity at 1.5 hours. That's 2.41. And lastly, 0.5 times, and then the height of my rectangle is based on velocity at 2 hours. That's 3.25. So if I run all of this through my calculator, I find that Kim has walked approximately 5.065 miles. Now, we noted that this was going to be an overestimate. And this is an overestimate because we were using the right endpoint of each of our intervals and our function was increasing. So we can say that since v of t is increasing, that r sub 4, our right endpoint estimate using 4 intervals, is an overestimate. That is, Kim did not actually walk 5.065 miles, but that is less. So what we do know is that the actual distance that Kim walked is less than 5.065 miles because that was an overestimate, and it's greater than 4.315 miles because that was an underestimate. So now, because we know that velocity is the derivative of the position function, use what we know about Kim's velocity, that is v of t is 1.75 plus 1.75t minus 2t squared plus 0.75t cubed to find a function to represent her position. Use this function to find the value of s at 2 minus s at 0. So we know that v of t is equal to s prime of t. So that means that s of t is the antiderivative of v of t dt. So the antiderivative of v of t is the antiderivative of 1.75 plus 1.75t minus 2t squared plus 0.75t cubed dt. So s of t will be, integrating each term in our integrand here, is 1.75t plus 1.75 over 2 t squared minus 2 times t cubed over 3 plus 0.75 times t to the 4th over 4 plus c. So simplifying this up just a little bit, s of t equals 1.75t plus 0.875t squared minus 2/3 t cubed plus 0.1875 t to the 4th plus c. Now let's go ahead and compare s of 2 and s of 0 by subtraction. So first of all, s of 2 is 1.75 times 2 plus 0.875 times 2 squared minus 2/3 2 cubed plus 0.1875 2 to the 4th plus c. And what we want to do is we want to subtract from that s at 0. Well, s at 0 is 1.75 times 0 plus 0.875 times 0 squared minus 2/3 times 0 cubed plus 0.1875 0 to the 4th plus c. So we're doing this subtraction here, and so what we're going to end up with is what s2 minus s0 is. Okay, so we have 1.75 times 2 minus this term here is 0. So we get 1.75 times 2 plus, in s of 0, this is also 0, this is also 0, and this is also 0. So as I'm subtracting these corresponding components of the two functions, I'm getting 0.875 times 2 squared minus 2/3 times 2 cubed plus 0.81875 times 2 to the 4th. And notice here that I have my constant of integration minus my constant of integration. Those will add to 0, subtract out, they'll add to 0. They no longer are relevant in this particular problem. Now, if I run this value through my calculator, we can find that Kim actually walked 4 2/3 miles. You may have gotten a decimal form, 4.666 and so forth miles, which is 4 2/3 miles. Now, how do I know that this is the distance she walked? Well, I know that this is her position 2 hours into her walk minus her initial position. And so the difference between those two positions gives us the distance that she walked within those 2 hours. So if we were to compare what we just found, that the actual distance that Kim walked is 4 2/3 miles, to our previous estimates, we saw that using the left endpoints of each interval to do an estimate, we got 4 and roughly 3/10. and using the right interval, right endpoint of our intervals, we got roughly 5. And so you can see that the actual is in there, in between those two values, not terribly close, but a good estimate. Now, how might we improve our estimates? So remember that the error in our estimates was due to either overestimating or underestimating. So how might we reduce that overestimate error or that underestimate error? Well, we can do that by basically taking smaller intervals, and smaller intervals will produce less error. So we're not going to compute it, but let's just take a look at a visual of what that means. So here's a quick visual using left endpoints but smaller intervals. Instead of using 0.5 hours to create the rectangles, we could use 0.25 hours or a quarter of an hour. So notice by taking the number of intervals intervals and doubling them. So instead of having 4 rectangles, I now have 8 rectangles. I can reduce the error in my estimate. What we have shaded here in yellow is the error from the left endpoints using 4 rectangles. So compare that error to the error we will get using left endpoints with 8 rectangles or 0.25 interval. So in the first interval, we'll have this error. And notice in this next interval that we've eliminated that error and made this more accurate. There will be some improved accuracy in these third and fourth intervals. However, the precision of our graph just doesn't make it possible to see. In the next pair of intervals, again, in this 1 to 1.25, we can't really see a change. And because of the shape of the graph, we're not really gaining anything in this 1.25 to 1.5 interval. Notice that from 1.5 to 1.75, yeah, we're not gaining a whole lot more accuracy. We're still going to have some of this error occurring. However, when we get to this last interval, this 1.75 to 2, our error is only going to be this much, and we're going to eliminate that component of error. So the error being made is much, much less compared to when we had only 4 intervals and 4 rectangles. I hope you find this helpful.